Okay, so let's dig into this one. You know how LLMs are like really good at that whole needle in a haystack thing? Finding that one specific bit of info, even in like tons of text.
Right, superhuman recall. It's pretty impressive.
Exactly. Well, there's this new paper, AbsenceBench, Language Models Can't Tell What's Missing, and it basically flips that whole idea on its head. Turns out they're, well, surprisingly bad at seeing what's not there, what's been taken out.
Yeah, and that contrast is what's so fascinating, is they nail recall. But this paper shows even top models, like Claude 3.7 Sonnet, they only get around, 69, 70% F1 score?
Yeah.
On just identifying stuff that's deliberately missing.
Bro.
Which seems simple to us.
Totally simple.
Right. But it suggests this maybe fundamental issue with how transformer attention sees or doesn't see gaps. And that's got big implications for trust, evaluation, all that stuff, especially when you need things to be complete.
So what's the deal? We're going to dive into AbsenceBench today on AI Paper Podcast, look at why they struggle, and maybe why this blind spot is like baked into the architecture. You're about to get well informed. All right, so let's start by really defining the problem here. We've all seen how good LLMs have gotten, especially with long documents. That needle-in-a-haystack test, NIAH, right, where they find some tiny detail in a huge amount of text.
They've gotten incredibly good at that. Almost perfect sometimes.
But this paper asks the opposite question, which is kind of brilliant. It's like, what if the needle should be there, but it's gone? Can the LLM actually tell you, hey, something's missing here? That's what AbsenceBench is all about.
And it's super important because just knowing what is present isn't the full picture, is it? So AbsenceBench is set up to measure exactly that. Can the model spot the missing info? They give the model two things, the original document, and then a version where stuff has been deliberately taken out. The model's job. Generate the exact things that were removed. Nothing more, nothing less.
Okay. And it's not like those crazy million token context windows, right? You said it's medium context.
Yeah, that's right. It's more like 5,000 tokens on average. So significantly shorter than a lot of the extreme long context benchmarks. It's less about memory endurance and more about this specific absence detection skill.
So it's focused. What kind of missing information are we talking about? Did they use different types of data?
Good question. Yeah, they used three pretty different domains to make sure it wasn't just, one weird quirk.
Yep.
First up was poetry. Give the model a poem, then a version with lines missing. The task is to output only the missing lines. Like imagine taking lines out of "Do not go gentle into that good night." The model needs to spot exactly which ones.
Okay. Poetry. What else?
Then numerical sequences. So you have a simple sequence like 117, 121, 125, and so on. Then you give it a version like 117, 125, 129. And the model has to identify that 121, and maybe others are gone.
That feels like something a script could do easily. Why is it hard for an LLM? We'll get to that, I guess.
We will. It seems simple. And the third one is maybe the most practical. GitHub pull requests. Basically, looking at code diffs, you give it the original set of changes plus me lines, then a version where some of those changed lines are missing. And the model has to spot the absent plus or apt lines. This is super relevant, right? Like for checking merge conflicts or code reviews.
Oh, absolutely. If your AI code assistant misses deleted lines in a review, that's not good.
Exactly. And critically, they use the F1 score for evaluation.
Right. That matters because
it balances precision and recall. You can't just guess wildly or copy the whole original text. You get penalized for false positives saying something is missing when it isn't. You have to be accurate about only the omissions.
Okay. Makes sense. Clear problem, good test data, solid metrics. So how did they do? You said surprisingly challenging. Lay it on us.
Yeah, challenging is putting it mildly. They tested 14 LLMs, the big names like Gemini 2.5 Flash, Claude 3.7 Sonnet, GPT-4o, and open ones like Llama 4 Maverick, Mixtral 8x7b. And across the board, the performance was underwhelming. The best scores, even using extra thinking time, were just around 70%. Gemini 2.5 Flash hit 71.2%. Claude 3.7 Sonnet got 69.6%.
70%? It's okay, but not the 99% we see elsewhere.
Not at all,
No.
especially compared to Needle-in-a-Haystack. That's where it gets really stark.
Okay, tell me about that comparison. How big was the drop?
Massive. Take Mixtral 8x7b Instruct. It apparently gets a perfect score on NIAH tests at similar context lengths.
Perfect, okay.
On AbsenceBench, its F1 score was 14.7%.
Wow, 14%? That's barely working.
Pretty much. And on average, across all the models they tested, there was a 56.9% drop in F1 score, going from finding things present, like NIAH, to finding things absent, AbsenceBench.
Almost a 60% average drop. That really hammers home how different this task is for them.
It really does. It suggests absence detection isn't just a harder version of recall. It might be a fundamentally different and weaker capability for these architectures.
So what about throwing more compute at it? You mentioned thinking mode. Did that help much? Worth the cost?
It helped a bit, but maybe not enough to justify the cost.
Yeah.
For models like Gemini 2.5 and Claude 3.7 that have this, it boosted the F1 score by about 8% on average.
Okay, 8% isn't nothing.
True, but listen to this. To get that 8% boost, they generated on average 8,000 extra thinking tokens per task. Remember, the average document size was only 5,000 tokens.
Wait, so they generated more thinking tokens than the actual document length? By a lot.
Yeah, nearly 3 times the document length on average. Now,
Serious?
2.5 Flash was even higher, almost 6 times the length in thinking tokens.
Wow. So they're really churning internally, maybe trying to reconstruct everything just to spot the gaps. That seems wildly inefficient.
It does suggest a brute force approach rather than an elegant solution, yeah. It's computationally expensive for a modest gain.
Interesting. And what about the classic closed source versus open weight battle? Any clear winner here?
Generally, the closed source models did perform better overall on AbsenceBench, yes. They got higher F1 scores,
There's always a but.
but they also tended to use significantly more of that thinking time, about 42% more thinking tokens on average than the open weight models.
So better results, but again, potentially higher computational cost and maybe more internal effort to compensate.
Exactly. It points towards this task being universally hard, even if some models have found slightly better, albeit costly, coping mechanisms.
Okay. And does making the haystack bigger, the context longer, make finding the missing needle harder, even in this medium range?
Yes, it seems so. Longer context length generally led to lower performance. This effect was clearer in the poetry domain, actually. There was a noticeable correlation there.
And that's different from NIAH again, right? Where length only matters at really extreme scales.
Precisely. With NIAH, problems usually only crop up way out past 100,000 tokens, sometimes millions. Here, even going from, say, 3,000 to 7,000 tokens within this medium range seems to increase the difficulty. It reinforces that the challenge isn't just scale.
Okay, now for the part that really baked my noodle reading the paper. The rate of omission. My gut feeling is fewer missing things, easier to spot, right? Like finding one missing book on a shelf.
That's what you'd think, isn't it? But the results were the complete opposite.
Seriously. So more missing stuff makes it easier.
Counterintuitively, yes. A lower rate of omission, meaning just a few things missing here and there, resulted in worse performance.
How does that work?
Well, the hypothesis is quite interesting. If you have a high rate of omission, like a whole chunk of a poem or a long string of numbers missing, it creates a really obvious break in the pattern. The model might kind of fall into the gap and keep generating until it hits the next present element. It's like a big hole, easy to see.
Okay, I can visualize that.
But if the omissions are sparse, one missing line here, one missing number there, they create smaller, more frequent disruptions to the flow. It might be harder for the model to track all these little gaps scattered throughout the text compared to one big, contiguous missing section.
Like finding lots of single missing bricks versus a huge hole in the wall. The small ones are harder to keep track of.
Exactly that analogy. The sparse gaps seem to interrupt processing continuity in a way that's more confusing for the model.
Okay, that's fascinating. So it really feels like this isn't just hard. It might be fundamentally misaligned with how transformers work. What's the core idea behind why this is so tough for them? The paper dives into the attention mechanism itself, right?
It does, and that's probably the most crucial insight here. The hypothesis centers on the transformer's attention mechanism. Basically, attention works by looking at relationships between tokens, words, numbers, pieces of code. It calculates scores based on queries, keys, and values associated with these tokens.
Right, finding relevant connections.
Exactly. But what happens when the information is simply absent? There's no token there. There's no specific key representing the missing thing for the attention mechanism to latch onto. It's trying to attend to, well, nothingness. And the mechanism isn't really designed for that.
So it needs something concrete to look at.
That's the idea. And the proof they offer is really compelling. It involves using placeholders.
Ah, right. Where they explicitly marked the gaps. Tell us about that experiment.
So they ran the tests again. But this time, in the modified documents, instead of just deleting a line, they replaced it with an explicit placeholder string. Something like missing line, or just a row of underscores.
Just a symbol saying something was here.
Precisely. And the results were dramatic. Putting in these placeholders boosted the average F1 score by a massive 35.7% across all the domains.
Wow, over 35% improvement just by marking the empty space.
Yeah. Llama 4 Maverick, for example, saw its score jump by over 54%.
That's incredible. It really does suggest the problem isn't understanding what was removed, but literally just noticing the gap itself.
Exactly. It strongly implies the self-attention mechanism struggles to anchor or process information that isn't explicitly represented by a token in the input. Give it a token, even a placeholder, and it does much better.
It needs that signpost that X marks the spot, even if the spot is empty. Okay, that's a huge insight into how these things operate. So if LLMs have this fundamental blind spot for absence, what does that mean practically? You mentioned LLM as a judge earlier. If it can't see what's missing from an answer based on a rubric, that's a problem.
It's a huge potential problem. Think about all the places we need not just accuracy, but completeness. Grading, like you said. If a student just doesn't address a rubric point, the LLM might overlook that omission. Legal reasoning, missing a key fact, a clause, a precedent because it wasn't explicitly mentioned, that could lead to seriously flawed analysis.
Yeah, high stakes there.
Code review, too. Missing deleted lines in a diff could let bugs slip through. The paper explicitly calls this out for merge conflicts, and even misinformation or propaganda analysis. Often, the most effective manipulation isn't outright lies, but strategic omissions of context or inconvenient facts. If the AI can't spot the missing pieces,
it misses a huge part of the picture. The paper's quote about needing to recognize uncovered rubric elements really hits home. It seems foundational.
It really does. It's capability we might have implicitly assumed they had, but AbsenceBench shows it's a major weakness.
So stepping back, what does this tell us about LLM intelligence more broadly? Is this just a bug or something deeper?
The paper argues it might be something deeper, suggesting LLMs have a kind of novel intelligence that isn't just a scaled-up version of human thinking. Humans are generally pretty good at noticing absence, right? We notice the missing keys, the silence where there should be noise. But LLMs, while being superhuman at certain complex tasks, NIAH, math, whatever, fail spectacularly at the seemingly simple task of noticing absence.
So the shape of their intelligence is different, as the paper puts it, with weird peaks and valleys compared to ours.
Exactly. They call it an LLM-specific cognitive bias. It's not that they're just less smart overall. Their intelligence profile is just different. And this is a clear blind spot.
LLM, specific cognitive bias. That's a great phrase. So where do we go from here? How do researchers even start to fix this?
That's the million-dollar question, isn't it? The paper suggests a few directions. One is exploring new architectures. Maybe we need mechanisms fundamentally different from standard attention, ones designed explicitly to handle, represent, or infer missing information.
Moving beyond just attention.
Potentially, or augmenting it significantly. We also need a better mechanistic understanding, really digging into why current attention struggles. What are the specific mathematical or structural properties causing this failure? And then moving beyond just simple missing lines or numbers, future work needs to look at more complex semantic absence, like spotting omitted reasoning steps in an argument, or missing evidence needed to support a claim, or implied information that isn't stated. That's much harder, but crucial for real-world understanding.
So developing absence-aware architectures, it feels like a whole new dimension for evaluation, too.
Absolutely. Current benchmarks are overwhelmingly focused on what models can do, what information they can retrieve or generate. AbsenceBench highlights the critical need to also evaluate what they can't see, what they miss. It's about understanding the gaps in their capabilities.
So wrapping up, it's pretty clear that this seemingly simple task, just noticing what's not there, is actually a massive challenge for even our best LLMs. It's a really fascinating result that makes you reconsider the fundamental mechanics of these AI systems we rely on more and more.
It really does. And it leaves us with a pretty critical thought. As we push AI into more important roles, how can we ensure they're truly trustworthy if they have this basic difficulty understanding absence? Maybe tackling this very problem, focusing on how to make models aware of what isn't there, could be a key step towards building more robust, reliable, and maybe even generally capable AI. Makes you wonder, what other fundamental aspects of understanding are LLMs still missing?
Something definitely worth thinking about. That's all for this deep dive into AbsenceBench here on AI Paper Podcasts. We hope this gave you some valuable insights to chew on. Until next time.